Anyway, for full wave bridge rectifier, this is what you're going to see in lab, and you have to fill it out. Now, clearly, they've already filled out what you'd expect to see across the load. We want to look at what you're going to see across each one of the diodes. So what I'm going to do is I'm going to go over here, and we're going to put, let's see, diode 1, diode 2, diode 3, and it looks like I need another line, don't I? So we're going to extend the page, and we're going to go as diode 4. Whoop. Okay, so there's our 4 diodes, and we're going to go through each step so you guys can clearly see how this thing breaks out. So, looking at the first half here, right there, what I'm going to do is I'm going to assign a polarity for each one of these. So, when the AC supply is positive, we're going to call this positive and that negative in the first alternation, okay? Now, this is where, and this is very important when you guys do kind of a tracing move. This point at part A is positive right there. That means the anode of diode 1 is positive with respect to the cathode. What does that mean for the cathode of diode 3? Is it positive or negative? It's positive, right? Isn't it the same point? It's just a chunk of wire. That means right now that's positive. Well, that means the anode has to be negative, right? So if this wire over here is negative, that means point B is negative. So we can stick a negative sign there and a negative sign there, and that means the opposite is true. So that makes that positive and that positive. That's step 1. If you get this right, you're not going to have a problem. So when we apply this source, you can see that diode 1 is forward biased. Which other diode is forward biased? 4. Okay? The other 2 are reverse biased. So let's forget the load over here for a second. We know that this is the load. Okay? Let's not look at the load for right now, but let's just take a look at diode 1 and 4. So you guys both said it's going to be conducting, right? So let's write that in. Diode 1 is conducting. Diode 4 is conducting. That we know for sure. We don't have to go any further. We know that those are acting like a closed switch. So now what we're going to do is we're going to go up here, and we're going to follow some current flow. Current starts here. It gets to point A. It has a choice. It can go up through diode 1, or it can try going down through diode 3. Which one is it going to take? Diode 1. The only one it can, because diode 3 is reverse biased, acting like an open switch. So it's going to flow to here, then it's going to get to this point. It has 2 choices. It could go through the load, or it can try going through diode 2. Which one is it going to take? The load. Why not diode 2? It's open. It's acting like an open switch. The only path it can take is through the load over to here. Now again, it gets to a choice. It can try going through diode 3 or diode 4. Which one's it going to take? 4, because diode 3 is acting like an open switch. So at that point, we know that the load sees, as you can see it demonstrated, the load is going to see peak source voltage. Now, we haven't applied any numbers here, and I'm not going to. I think you guys get the idea on how to take your RMS and divide it by 0.707 to get there. I'm not going to repeat that. So that is your peak source voltage at this point. And again, that means diodes 1 and diodes 4 were conducting. At that same time, what was diodes 2 and 3 doing? They were blocking. Now, if they're blocking, aren't they blocking the reverse voltage of this? Yeah. So we would see this. Oops, wrong one. Here. And here. Okay. The load sees the positive voltage the diode was having to block the opposite voltage. All right, that's step one. Is everybody good to this point? All right, now let's see what happens in the second alternation. So now I'm going to go to blue. Let's change this to blue. And I want to make sure that I am dealing with thin. Good. Okay, so I have to erase some stuff here, and we're going to look at what happens. Again, I'll put in the diode numbers. So this is diode 1, 2, 3, 4. And now we're in the negative alternation. That means that this guy is negative and this guy is positive. Now we have to follow that through. Well, let's start with the positive guy. That automatically means that B point is positive. That means that that's positive and that's positive, which means the other side of those are both negative. They're forced. I might highlight this. They are forced to be negative. Okay? If this is negative, that means that's negative and that's negative. That's the same point, which means the opposite on either side of that is positive. Now, take a look at your 4 diodes. Which 2 are acting like a closed switch? 2 and 3. So, now we're going to go over here and we can say, okay, now diode 2 is acting like a closed switch, so is diode 3. Well, if they're acting like a closed switch, here's how current flows. So now current goes like this. It starts there, it gets to point B, it has 2 choices. It can either go through diode 2 or diode 4. Can it go through 4? No, because it's acting like an open switch. So current now goes through diode 2 like this. It gets to point C. It can't go through diode 1 because it's acting like an open switch, which means it has no choice but to go through the load. Okay? It gets to this point here at point D, and it has to look for the closed switch. Well, it can't go through diode 4. That's reverse bias. The only place it can go is through diode 3 and out. So that means that diode 1 and 4 were blocking the reverse voltage. And so if we put that in, they were doing this. Okay? Makes sense? And then it carries on and the cycle repeats itself. All right? I'm not going to go through the next 3. Hopefully you get it. Now, I want to just back up and ask you this question. What happens if we had a short in one of these diodes? What's going to happen? Anybody want to venture a guess?
It would turn into like a half wave.
Okay, it would turn into a half wave for a fraction of a second. I would agree. Who else wants to take a guess? There's no wrong answers here, you guys. I'm going to give you the right answer. I just want to see if your guys' train of thought is where it needs to be. You're on the right track. Blow a hole in what? In the load? All right, I'm going to help you out a little bit along those lines. What if I did this? What's that? That's an overcurrent device. So let's take a look now. So this current has gone through diode 2. It couldn't go through 1 because it was acting like an open switch, right? So it had to go through the load, and it got to this point D here, and it had a choice. It could either go through diode 3 or it could go through diode 4. Now, normally, diode 4 is acting like an open switch. But all of a sudden, it isn't. All of a sudden, there's a short across it. Is current going to flow through the resistance of diode 3 or take the easiest path? It's going to take the easiest path. Don't we have a short, dead short there? Yep. Okay, so dead short is going to trip your overcurrent device. So that brings us to my last question. How much voltage are the diodes required to block? Peak what? Line, good. Peak line voltage. We don't know what that is here, but it has to block peak line voltage. Okay? You guys get this, you're in good shape. Any questions on this before we move into three-phase? All right. So I think I have a bit of a review slide coming up here. Let's take a look. Now this just tells you how we get our average voltage. So if I said to you, what is that average voltage across the load? Again, you notice that unlike the previous rectifier, what was the difference in the voltage across the load? Did it see half or full? The last one saw half, this saw full. Take a look at, here's your load. On the previous one, it was only across half the windings, right? Not here. It's across, it sees full peak voltage through both cycles. All right, which gives us an average. So we don't have to divide by 2 like we did last time, do we? Last time we had to take peak, divide by 2, and then multiply it by 0.637. On this one, we don't. We simply take peak and multiply it by 0.637, or 2 over pi. And that gives you your average voltage. So if I was to ask you a test question and I said true or false, does the center tap full wave rectifier provide more average voltage than the bridge rectifier? What would you tell me? False. Good. Okay. This one provides higher average voltage. You don't have to divide by 2. It's across the full winding. So, review of this. Full wave summary. Each diode carries half of the load current. Or we could say carries full load current half the time. Means the same thing, right? Good. Peak load voltage is equal to peak source voltage. That's the difference from this one to the last one. Each diode must block peak source voltage. That's similar. The frequency of the load is twice that of the supply, also similar to the last rectifier. To calculate the average load voltage, simply multiply the peak by 0.637 or 2 over pi. Good. All right, three-phase half-wave rectifier. Now, before we get into evaluating this, when you look at this, what do you notice is the difference between the load and the diodes as far as voltages are going to be concerned here? Yeah, load's phase voltage, right? Because we have a neutral involved. The diodes aren't. Okay? If I had a short here, from here to here, does that have anything to do with a neutral? No, that's a line-to-line short, isn't it? And if I have a short across the load, that's a phase voltage. Okay? Good. So that's the first thing we need to make sure you see is the difference on the half-wave rectifier. Now, three-phase, of course, we have 3 voltages contributing to the current that's going to flow through the load. Now, if I can fit that entire thing on the screen. Let's look at this point right here. So I'm going to just do this. I'm going to maybe put some colors in here to help us out. Red, black, blue. So this is red. That's black, and then let's do blue. So you can, so there's blue, there's black, there's red. Okay, just so we can keep track of the 3 different phases we have. Okay, I don't know where the hell that came from, but let's get out of that. So, we're going to look at the red part right here. We want to look at this. That is phase A. So phase A, when you look at the peak of this, is saying it's 10 volts. When we look at the same point in time, phase B and C are only at 5 volts, but in the negative. Which one of those 3 voltages has the strongest electrical potential? A does. And it's positive. So is it fair to say, if we go in here right now, we could assign some polarities and say there's absolutely no question A has the largest potential period, and it's in the positive. So we know that that one is forward biased. Now at that same point in time, we know that B and C are in the negative. So what does that automatically what I'm going to touch my screen here. What does that automatically do for the polarity of diodes B and C? It's reverse bias. So negative, positive, okay? That means at this point in time, phase A is conducting. So current flows through it to the load and back out. Therefore, the load will see peak phase voltage. Okay? Not peak line, peak phase. And hence why we see this pump right here. Now, let's look at voltage Bn. When voltage Bn, at this point right here, and this is black, voltage Bn now all of a sudden has the highest potential or voltage. And it is the highest positive potential. So, we got to erase all these and reevaluate all three diodes. B, no question, is the big dog, so it's going to be, positive and negative. Both of the other two are in the negative quadrant, so we know that they are reverse bias. Okay. That means that phase B is going to conduct and flow through the load. Okay. Now we can say the same thing when we get over to phase C. Now all of a sudden it has the highest positive potential, and so therefore its anode will be positive with respect to the cathode, and the other two are reverse bias. Now I'm just curious, is anybody going to ask me about what happens in between? There's usually always one student that asks, or at least is thinking it. So what happens in between? These are easy to see, aren't they? Because we have each phase has the highest positive potential, pretty straightforward. What about in between? This is part of your handout, you guys. Because in between, it's not so cut and dried. And I'm hoping that this may help you with that a little bit. So let's take a look at right here. And again, I'm going to put some colors. So black is this guy, blue is this guy, and red is this guy. So at this point right now, phase A and phase B are both positive. Right at that point in time, right here. They're both positive. So can they both be forward biased? Well, if they did, wouldn't we have a dead short? Yep. So they can't be. The very first thing I want you guys always to look at is not specifically which one is positive, but which one of the phases has the highest what? Electrical potential. Which one of the phases, positive or negative, which one has the highest electrical potential at this point? The black guy. Is that black? Nope. C, blue guy. It has 10 volts, albeit in the negative, it has 10 volts. So what can we say for sure about phase C? Is it forward biased or reverse biased? It can't be forward biased because we're in the negative. But what we can say for sure, there is no question, it is reverse biased. What's going on here? There we go. It is reverse bias, and that's our blue guy. So we can say that no question, that is reverse bias. It has the highest electrical potential. So that leads us to this other point right here. Now, if we look at the left side and look at phase A, right before that exact point in time, it was forward biased. It was like this. Phase A was like this, positive, negative. Okay, and that meant this was negative, positive. As soon as phase B is even a microvolt higher in electrical potential than phase A, it becomes forward biased. So that all of a sudden becomes forward biased like this, which forces, and the word force, even though A is still technically positive, so I just want to do this. And if you guys, I don't know if you guys can see it. So at this point in time right there, can you guys see that back there? It's probably looking pretty small. Is it fair to say that A, which is what I'm making reference to, is still positive? Sure, it's still above the reference line. So you would think, well, that must mean it's forward biased. No. The one with the highest electrical potential positively is forward biased. So at that same point in time right there, you can see phase B has a higher electrical potential. That forces A to become reverse bias. And that's what that handout they gave you kind of goes through that. But I wanted you guys to get a foundation for how that actually works. So for a fraction of a second, and I'm talking like a picosecond, they are technically both forward biased, but it doesn't take more than a picosecond before one of them has a higher electrical potential and becomes forward biased. Okay? Is that lunchtime? Is my watch right? I've got 1:45. Is that correct? Yeah? All right, let's carry on with this tomorrow. So you guys should be able to start into your rectifiers today. Hopefully that'll give you a foundation for where we're headed. Because then if they